So, hi guys, welcome to Garuda's Gate Academy. So, today we'll be looking at the gates and then we'll be looking at Boolean Algebra also. Okay. So, here I'll just brief all the gates, and in some other video we'll be looking at each and every gate. So, these are the gates that we have in digital logic. So, first one, AND gate. The functionality of AND gate is if you provide A and B signal, then it would AND it. AND it in the sense, so these are the signals, okay? So, or inputs, two inputs. So, if inputs are 2, then what are the possible cases? Both inputs can be 0 or 0 in the sense, see, 0 or off is same, 1 or on is same, okay? You can write like this. Or sometimes it is referred as false, it is referred as true, okay? So, since we have only two signals, we'll have 0 0 and 0 1, 1 0, 1 1. By practice, you'll come to know how to write all the inputs. If there are 3 inputs, then you will have 8 possible cases. Okay. So now we shall see ANDing of 0 and 0. ANDing of 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Okay. So if you AND 1 and 1, then only it will be 1. Otherwise, in all the cases, it will be 0. Or else you can say like this. If at least a single 0 is available in the input, then output will be 0. Okay. So in order to get output 1, you have to have all the inputs as 1. Okay. In the case of AND. Okay. This is the AND gate. Okay. So see here, it is OR gate. So OR gate is like when you OR 0 with 0, it will produce 0. When you OR 0 with 1, it will produce 1. 1 OR with 0, 1. 1 OR with 1, 1. Okay. So in order to have the output as 1 in the case of OR gate, you will be having at least single 1 in the input. If you are having single 1 in the input, then you will be having 1 as output. So if you see here, we have 2 ones, so no problem. So here we have single 1, so output is 1. Here we have 1, so output is 1. So in the OR gate, if you have any one of the inputs is 1, then you will have the output as 1. If both of them are 0, then only it will be 0. That is the case for OR. Okay. So complement. Complement is just negating it. Like if you give A, it will produce A bar. If you give B, it will produce B bar. Likewise, if you give 0, sorry, so see here, A is 0, then A complement will be 1. If, no, this is also same, right? So actually, a single input can have only 2 signals, right? 0 or 1, okay? Here we have taken twice this thing, so no need to write this once because already we have denoted the output for that thing, okay? So, for 0 it will produce 1, for 1 it will produce 0. That means it just produces the opposite signal. So that is regarding NOT gate. NOT gate is also called as inverter because it will invert the signal. And the other one is buffer. So buffer is like it will produce the same signal as the input. Like if A is 0, then output will be 0. If A is 1, then output will be 1. That is the buffer thing. So here I have not mentioned any column for buffer because so A output will also be A. So there is no point in mentioning that thing here, right? So up to here, students will remember properly, and they'll start forgetting these gates. And these are the important gates actually. Okay, so you should be more careful while dealing with these two gates like XOR and XNOR. Okay, so we'll discuss about NAND gate. Okay, in the name itself, it is mentioned that NAND. Okay, NAND. NAND is not plus and, which is NAND. Okay, so that means you can write AND gate, and if you apply complement, then that would be NAND gate. Okay, so see here, this is AND gate. If you are putting some negation here, then that becomes NAND gate. So compare this one, AND gate and NAND gate. So if you compare both of them, just a small circle is the difference, right? That circle is for negation. That is how it will become NAND gate. And NOR gate is also same as OR gate. I mean in terms of representation. Okay, so this is OR gate, this is NOR gate. Only difference is this small circle. Okay, and NOR gate also you can write like NOR is equal to NOT plus OR, or OR plus NOT. You can write like that as well, right? Yeah, and we forgot to write the table. Okay, so NAND gate. So NAND gate is just complement of AND, right? So what is AND? This is the AND. So just complement this thing. 1, 1, 1, 0. This is NAND. So that means if A is 1 and B is 1, then and NAND will be 0. In all the other cases, it will be producing 1, even in the case of 0 and 0, right? Now NOR gate. Okay, NOR is simply complement of OR. OR is here, right? So 1, I'm just complementing it. 1, 0, 1, 0, 1, 0. Okay, so NOR gate will produce 1 only when both of the inputs are 0. In all the other cases, it will be 0. Only if the input signals are 0, both of the signals, then only it will produce 1. What is that gate? NOR gate. Okay, this is NOR. This is NAND. Okay. And the most important part of this gates concept is these two gates. Okay, people usually forget these things, so try to be more careful and try to remember these two gates. Okay, and you will get most of the questions from XOR or XNOR gates. So if you see that XOR or XNOR gates, XOR in the sense exclusive OR. Okay, so if inputs are 0 and 0 or 1 and 1, in both of the cases it will produce 0. In all the other cases it will produce 1. Okay, one more time. In the case of 0 and 0 and 1 and 1, that means same set of input signals like 0, 0, 1, 1. Okay, so if the same set of signals are given, then it will produce 0. If the input signals are different, then it will produce 1. So that means this gate can identify whether there are even number of signals in the input or odd number of signals in the input, because if there are two zeros, it is producing 0. In that way we can understand that there are same set of signals in the input. And in this case also we have two ones here and it is producing 0. So we can understand that in the input there are same set of input signals. If it is getting 1, that means the input signals are different, 0 and 1, 1 and 0. So that is how we can understand, like, and this is very useful while counting, right? So 0 plus 0 is 0, 1 plus 1 is not 0, it is 1 0 actually. 1 will be in the carry. Okay, so while getting carry, this will be useful. XOR gate. And in this case, 0 plus 1 is 1, 1 plus 0 is 1. Okay, and this XOR gate is just complement of this thing. Just you can complement it 1, 0, 0, 1. And you can understand this one, like if in the input there are two same signals coming, then it will show 1. If different signals are coming, it will show 0. This is also can be used for identifying whether there are same set of signals in the input or not. Okay, it is just an example sake I'm telling you. So these are the important gates that we have in digital logic, and you should be remembering all these gates and its functionality. Okay, so because this will be useful while we are dealing with Boolean algebra. Okay, and now let us discuss the Boolean algebra. So general algebra, we have seen it in 10th standard, plus 1, plus 2, and so on. But Boolean algebra is somewhat different from ordinary algebra. Boolean algebra deals with 0 or 1, true or false. Okay, so these are the properties that we have in Boolean algebra. And one more thing, Boolean algebra is also called switching algebra. Okay, so these are the properties that we have in switching algebra or Boolean algebra. Let's start with this one. X plus 0 or 0 plus x will be x, right? So if ORing is done between x and 0 or 0 and x, then the final output will be x. Okay, this can be understood like this. There is x and 0. This is for output. I'm just drawing the truth table. We have discussed about this truth table in the earlier of this video, right? I have placed some gates here and some gates there, and in between I have drew the truth table, right? So that kind of table is this. So here x is a single input, so an input can be 0 or 1, right? So what are the possible cases of 0? Oh, sorry, what are the possible cases of x? 0 or 1, right? So in all the cases 0 will be 0 only. So here we are ORing it, right? So we have discussed about OR gate. OR gate will be false when 0 and 0 is input. In all other cases it will be 1. So this is equivalent to this one. That means x plus 0 is equal to x. If you perform 0 plus x will also be x. Okay, so that is the meaning of this one. So same goes with x into 1, 1 into x, that will be x. Here AND gate, right? So if you AND with 1, so if it is 1, always input will be 1, right? So 0 and 1 will be 0, 1 and 1 will be 1. So 0 and 1, 0, 1, which will be equal to x. Output is equal to x. So that is why x into 1 is equal to 1 into x is equal to, sorry, not into, x and 1 is equal to 1 and x is equal to x. Okay, so coming to this commutative law or property, this is like x plus y is equal to y plus x, which means, so for OR gate, let us suppose there are two inputs over here. Okay, this is x, this is y, output will be x plus y, right? So here if you change the input signals, so first you are giving y and second you are giving x. So even though if you change the order of the input signals, if the output is same, then that is said to have the commutative property, or it is following commutative law. Okay, so x plus y is equal to y plus x into y is equal to y into x, not into, sorry, x and y is equal to y and x. Okay, here we always talk about OR gates and gates. Okay, whenever there is plus, that is equal to r. Whenever there is dot, that is equal to and. Okay, so yeah. Now associative law. So associative law is x plus y plus z is equal to x plus y plus z, which means whatever the associativity is followed, whether it can be right associativity or left associativity followed, both of the results are same, then it is said to have the associativity property. So this one also, here just we have replaced plus with dot, plus with dot, plus with dot, plus with dot, right? So this is just a dual function of this one. So this one is a dual function of this one. What is a dual function first of all? So see here, x plus y. So what is the dual function of this? This will be x dot y. So what does dual function do? Dual function replaces plus with dot, dot with plus, 0 with 1, 1 with 0. Okay. So even though if you replace them with this ones, if the result is not changing, then that would be dual function. Now comes the trickiest and most important distributive and De Morgan's laws. X dot y plus z is equal to x dot y plus x dot z. So this can also be framed as dot is distributive over addition, or plus is distributive over dot, dot is distributive over plus, like that, right? So x dot y plus z is equal to x dot y. So see here, x dot y and y dot z. This is similar to ordinary algebra as well. Okay, but this one, the property which we're going to be discussing right here, this is not available in ordinary algebra. Okay, this is plus is distributive over dot. So wherever you find x plus y dot z, which can be x plus y and x plus z. This plus is acting as a dot here. So this is the most important property that you have to remember. Okay, and this is not available in ordinary algebra. And the next comes De Morgan's law. X plus y whole bar is equal to x bar dot y bar. And here also, if you observe, plus is replaced with dot. Here dot is replaced with plus, and everything holds. Okay, so this one is dual function of this one. Okay, and the next one is absorption. So this property or this law is named after absorption because this is absorbing this part and it is equivalent to x again. So if you replace plus with dot, and here it is dot, right? So this is a dual function of this. Okay, so here are some of the properties we have. X plus x bar is 1, because if you see the truth table of that, x will be having only 2 possible inputs, and x bar will be just opposite of this, right? So if you perform OR operation, it will always be 1, right? X plus x bar, it will always be 1. Okay, if you perform an AND operation with that, there is 0 in every case, so that will be 0 always. So that is the property of this. And x plus x1, every property listed over here, we can draw the truth table and we will know what are the results. Okay, x plus x will be x again, x into x will be x again, x plus 1 will be 1, and this one we're going to use in the problems as well. So x plus 1, right? 1 in the sense 1 will be 1 in every case. So 0 plus 1 will be 1. 1 plus 1 will be 1. So x plus 1 will be always 1. Likewise, x into 1 will be always, sorry, x into 0 will be always 0, because here AND operation is going on. 0 will not change in any of the situation. So if there is 0, AND gate will always produce 0. Okay. So if it is x plus 0 that we have discussed over there, if it is x plus 0, then that would be x. Okay. So these are the properties that we have in Boolean algebra, and we had a brief discussion on logic gates as well. So this is regarding Boolean algebra and logic gates, and next we're gonna see Boolean functions.